everyone, thank you for being here today. We are from Group H. Today we are going to presenting on design of reactor separator system for methanol production plant. From Group H, my name is Joey and these are my group members, Phong Ruan, Asma, Tana, and the last one is Mahendra. Today I will be presenting the introduction of our project on the design of an integrated reactor and separator system for methanol production. Methanol is an important platform chemical that is widely used to produce formaldehyde, acetic acid, fuels, and many other industrial chemicals. As industries move towards greener technology, producing methanol through carbon dioxide or CO2 hydrogenation has become an attractive approach because it supports sustainable manufacturing while helping to reduce carbon emissions. Since industrial applications require methanol with a purity of at least 99.5%, an efficient purification process is also essential. Therefore, our project focuses on designing an integrated reactor and separator system. For the reaction engineering part, we selected a suitable reactor, catalyst, and operating condition to maximize methanol production. For separation process, we designed an absorption-based purification system to achieve 99.5% pure methanol. Therefore, our project objective is to design an efficient methanol synthesis process, evaluate reactor performance, included conversion, yields, and selectivity, develop an absorption system for methanol purification, and last but not least, integrate the reactor and separation units into a sustainable production process.
Let's start with the design basis for our material balance. We set a target of 500,000 tons of methanol per year, produced continuously over 330 operating days, that's 7,920 hours annually. Our single pass carbon dioxide conversion is fixed at 30% based on the equilibrium limits of this reaction, and we feed hydrogen and carbon dioxide at the stoichiometry 3:1 ratio, entering the reactor at 247.3 Celsius and 89 bar. Converting that annual target to an hourly basis gives us a production rate of 60,131 kilograms of methanol per hour. This single number is what everything else in the material balance is built around. Every feed rate, every effluent rate, and the reactor sizing itself trace back to this target. Working from the target, we calculate our feed requirements. The reactor inlet needs 6,568 kilomoles per hour of CO2 and about 19,704 kilomoles per hour of hydrogen for a fresh total feed of roughly 26,272 kilomoles per hour. On the outlet side, since only 30% of the carbon dioxide and hydrogen react per pass, we are left with about 4,598 kilomoles per hour of unreacted carbon dioxide and 13,793 kilomoles per hour of unreacted hydrogen, alongside 1,970 kilomoles per hour of each methanol and water, formed in a 1:1 ratio. When we close the overall mass balance, inlet and outlet match to 99.9998%, confirming the numbers are internally consistent, and we also see the volumetric flow drop from 15,226 to 13,817 cubic meters per hour because 4 moles of gas break down to 2 moles of product.
On this slide, I will explain the reactor selection, operating condition, and catalyst used for our methanol production process. Our main reaction is the hydrogenation of carbon dioxide with hydrogen to produce methanol and water. For the reactor, we selected a plug flow reactor because it is the most suitable reactor for industrial methanol synthesis. Compared to a CSTR, a PFR provides higher conversion, minimal axial mixing, and continuous operation, making it more efficient for a larger scale production. It will allow better heat removal, which is important because methanol synthesis is a highly exothermic reaction. Next, we selected the CU the CuZnO L2O3 catalyst, which is the standard industrial catalyst for methanol synthesis. It offers high catalytic activity, high methanol selectivity, and good thermal stability, making it reliable for continuous operation. The reactor operates at an inlet temperature of approximately 247 degrees Celsius and outlet temperature 285 degrees Celsius, and the pressure of about 9 MPa, with a hydrogen to carbon dioxide feed ratio of 3 to 1. These operating conditions were obtained from our process simulation and are consistent with value reported in the literature. Overall, the combination of the PFR catalyst and selected operating condition provide efficient methanol production with a stable reactor performance. This slide explains how the reactor size was determined. First, we obtained concentration versus time data and assumed that hydrogen is present in excess. The reactor operates at steady state, follows power law kinetic, and has constant volume. Using the concentration data, we determined the reaction order and the reaction rate constant by plotting the kinetic data. From the graph, we obtained the rate law, which was then used to calculate the reaction rate at a different concentration. Next, we calculated the inlet molar flow rate conversion. Uh, These values were then used to construct the Levens pill plot, which is shown on the right side of the slide. The area under this curve represents the required reactor volume for a PFR. Finally, Simpson one-third rule was applied to calculate the area under the curve, giving the reactor a volume of approximately 1012 cubic meters. This reactor volume is sufficient to achieve the target methanol production while maintaining the desired conversion under the selected operating condition.
Now looking at how the reactor actually performs, carbon dioxide and hydrogen conversion both come out to be exactly 30%. Methanol selectivity is essentially 100% under our simplified reaction model, and yield, which is conversion times selectivity, is also 30%. In terms of reactor sizing, with a catalyst bed volume of 1012 cubic meters, we get an average carbon dioxide consumption rate of about 1.95 kilomoles per cubic meter per hour, a residence time of roughly 4 minutes, a gas Howley space velocity of 15 per hour, and a space-time yield of 62.4 kilogram of methanol per cubic meter of reactor per hour. These numbers are all consistent with what you expect from a high-pressure catalytic packed bed at this scale. So why only 30% conversion per pass? This isn't a flaw in our design, but it's the thermodynamic equilibrium ceiling of forced carbon dioxide hydrogenation at 250 to 285 degrees Celsius and 75 to 89 bar over the copper zinc oxide alumina catalyst. No matter how well we design the reactor, we can't push past the equilibrium ceiling in a single pass. That's why our process include a recycle loop. Unreacted carbon dioxide and hydrogen leaving the reactor are recovered and sent right back to the reactor inlet, which leaves our overall plant conversion from 30% per pass to more than 90% overall. Meanwhile, our selectivity of 100% reflects the simplified single reaction model we used. Real copper-based catalysts typically achieve 98 to 100% selectivity in practice, and the roughly 4-minute residence time we calculated is physically realistic for a real reactor at this scale and these operating conditions. So to summarize, 30% conversion isn't a limitation we fail to resolve, but it's a known equilibrium constraint that our recycle system is specifically designed to handle.
Hi, Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Tana, and for my part, I'll be speaking about isotherm and column design. So, for this design, we selected the Langmuir isotherm because it accurately represents the adsorption behavior of the type 3A molecular sieve, which has uniform adsorption sites. Using the Langmuir model, the adsorption capacity was calculated to be 214.6 milligram per gram. At the end, we designed a fixed bed adsorption column with an MTZ of 1.5 meters, a diameter of 0.5 meters, and bed height of 3 meters. The calculated residence time of 11.6 minutes provides sufficient contact time for efficient removal. Moving forward for the purification performance. It starts with a gas-liquid separator, which removes the unreacted gases. The methanol stream then enters the adsorption column, where the type 3A molecular sieve selectively removes water while allowing methanol to pass through. A dual bed system with thermal swing adsorption, or TSA, enables continuous operation by regenerating one bed while the other is in use. As a result, the process achieves the target methanol purity of 99.5%.
My name is Ruan and I will be presenting Chapter 3, which focuses on the design of the separator system for methanol production. The main objective of this separator system is to purify crude methanol to an industrial-grade purity of 99.5%. After the reaction process, the methanol stream still contains impurities, especially water. Therefore, an adsorption-based purification system is proposed to remove the remaining water while minimizing methanol loss. First, we identify the chemical species present after the reactor. Methanol is the desired product while water is the main impurity formed during the hydrogenation reaction. Although hydrogen, carbon dioxide, carbon monoxide may still exist after the reactor, they are assumed to be completely removed by the gas-liquid separator before entering the adsorption column. Therefore, the adsorption unit only needs to separate methanol and water, simplifying the purification process. The purification strategy consists of three main stages. The first stage is gas-liquid separation, where unreacted hydrogen and carbon dioxide are removed from the reactor effluent. The second stage is adsorption-based dehydration, using a fixed bed adsorption column. This column removes water selectively, allowing methanol to pass through. Finally, the purified methanol is sent to storage, while the removed water is collected for disposal or further treatment. Now for the adsorbent selection, type 3A molecular sieve was chosen. This adsorbent has a pore size of approximately 3 angstroms, which allows water molecules to enter while preventing the larger methanol molecules from being adsorbed. As a result, water can be removed efficiently with very little methanol loss. In addition, type 3A molecular sieve has high absorption capacity, excellent thermal stability, and can be regenerated for repeated use, making it suitable for continuous industrial operation. Now I will pass on to the next
For the
presenter.
friendly isotherm, it was used to estimate the adsorption capacity of the type 3A molecular sieve, giving a value of 1.79 moles of water per kilogram of adsorbent. So based on the water entering the system, approximately 6,927 kilograms of molecular sieve are required after applying a 20% safety factor. So after applying that 20%, the final design requires about 8.3 tons of adsorbent. Assuming 99% water removal, the remaining water concentration is very low, allowing the system to achieve the target 99.58% methanol purity.
Conclusion, this IDP project kind of successfully developed an conceptual reactor and separator setup for producing industrial-grade methanol. By blending the idea from reaction engineering, one and separation process to not just one side, a PFR with copper, zinc oxide, and aluminum oxide catalyst was picked for methanol synthesis because it offers strong conversion efficiency, better thermal handling, and it also worked well for continuous industrial production. The chosen operating condition seems to keep the reactor running steadily while still delivering the targeted methanol production rate and reaching a satisfactory level of carbon dioxide conversion. Secondly, to reach high purity methanol, a downstream purification system made up of a gas-liquid separation step followed by a fixed bed absorption column packed with type 3A molecular sheath was proposed. In practice, the absorption part effectively pull water out of the crude methanol stream. So, a methanol product with a purity of 99.5% or more can be achieved, while at the same time keeping methanol losses as low as possible. Also, adding a regeneration strategy helps keep the plant running in a continuous manner, and it strengthens the overall sustainability and of course of the whole process. Taken together, the proposed reactor separator setup looks technically workable and fairly efficient for methanol production. By tying reaction and separation processes together, the design boosts process performance, improve product quality, and support better resource utilization. It also gives a solid conceptual base for later industrial trials, plus for additional detailed process optimized down the road. That's all for us. Thank you.